Okay, hello everybody. My name is Dan Dixon, and welcome to this talk titled Regional Scale Fire Severity Mapping in the Northern Jarrah Forest with Google Earth Engine. So I'm Dan, and I want to say thanks to my supervisors, Nick, John, Sam, and Natasha. I think John is over there in the corner. I'm a student, a PhD student in geography at UWA. I'm interested in using GIS and remote sensing to ask ecological questions. In this case, part of my PhD mapping wildfires and prescribed burns over the last 16 years in the Northern Jarrah Forest, essentially taking post-fire aerial photos, using those images to train a machine learning model to then predict the severity of fire. This is the impact of fire on forest canopy at a 30 by 30 meter resolution using Landsat, mainly Landsat, and I'm going to dig into that. In this talk, first I'll go over the motivation, why I'm the one doing this work, get into the guts of how the fire severity mapping works, and then talk about some of the benefits of using Google Earth Engine, because I don't think I would have been able to do this project, at least within the amount of time I've been able to do it, without some of the resources from Google Earth Engine. This is a global scale image processing and GIS environment to ask really questions without scale. So what we've got is this Northern Jarrah Forest Fire Severity Mapper. We don't have a great acronym yet for this model. You know, if you've got one, let me know. We're working on it. But really, for each fire, wildfire, and prescribed burn in the last 16 years, those are DBCA fire polygons in the DBCA 060 data set. Thanks to DBCA for putting those data together. Those were open source. So I've taken those data and then created a fire severity map with Landsat for each of those fires. So quickly, taking a few steps back, why am I the one doing this? So last year I did a presentation on mapping flowering trees with CubeSat imagery. And so we use PlanetScope, which is a constellation of miniature satellites, and we essentially take an image every day or every few days and create some vegetation indices. And based on some observations that we took with drones on the ground, we built a model to then predict flowering abundance. And we did this because flowering is not just a bioindicator of forest reproduction, but it also provides nectar and pollen for a range of pollinators, birds, and biodiversity in general. So we're interested in forest phenology, the timing of these plant life cycle events in the Southwest. And we use Earth Engine for that. Really, it's a one-stop shop for loading up our data, processing it through, building this time series and then making the prediction of flowering. And just to give you a quick idea what that looks like, so this is on the visualization on the bottom right is the number of predicted flowering pixels over time from January 1st to March 10th. So this is just a 2-month window, and then you see that in the map on the right-hand side, there's this pulse of flowering that happens over about 2 to 3 weeks. And we can make these graphs because we have a prediction on each day in the time series. And so we're scaling up these data across the Northern Jarrah Forest, looking at Mary, which is, or Corymbia calophyll. This is one of the main eucalypt keystone species in the Southwest. And so with those data, we've been making some observations. So this is one flowering event in 2018. You may not be able to see it, but it's along the water edge. This is like Mundaring Weir. And our model is predicting these trees were flowering on this day and this year, but really nothing further inland. And then we just go back in time just 6 months, and there was this prescribed burn that went through this patch of bush with a bit of a range of severity, and this is impact to the crown, right? And so, again, the data that go in, originally, the fire data are just burn, yes, no, and some metadata like whether or not it was a wildfire or a prescribed burn. So we need to be working at this scale, at almost the crown or the block scale, to be able to pick up this difference in variation. So we want to then ask some questions about some of the drivers of flowering. So we have climate and topography, but really this fire question time since fire and severity of that last fire. So we can get the time since fire with the DBSA polygons, but we then need to go in and say how severe was this fire, because there's going to be quite a range and impact on phenology depending on severity. And so we've got this model with a few objectives. First, build the model and estimate fire severity with Landsat data. This is a 30 by 30 meter resolution. Validate across a range of conditions. I'll show you we validate across different prescribed burns across different seasons, spring, winter, and autumn prescribed burns and wildfires. So it needs to be kind of generalizable across a range of different fire types. And then we apply that model to 717 fires, about 1 million hectares of burnt area over the last 16 years. Because we want to then go back and say, we have all this flowering data, all this phenology data, and go back to different areas that were burned at different times, at different severities, and ask questions about how they impacted phenology. So this is our response variable, what we're trying to predict in the model. It's just 5 categories, ranging from unburnt to canopy burnt. Category 1 is unburnt or mostly unburnt. Categories 2 through 4 range from just a range of canopy scorch. And then category 4 and 5 would mostly be called high severity. And these categories are the same response variables as those used in a couple models over east in Victoria and New South Wales. And we've done that on purpose to create some harmonized data sets that can be used to ask questions about fire severity broadly across environments, across regions. So that was Luke Collins and Rebecca Gibson in Victoria and New South Wales. And they're predicting severity really with the same categorical scale. And so for each DBCA fire polygon, we take that polygon and we really only need 2 bits of information using Earth Engine. We need the geometry, the shape, and we need the date of the fire. And then we can delineate the pre and post-fire image composites, which would be composites of all of the Landsat images intersecting that fire polygon before or after the fire date. And then we take the median composite value of all of those pixel values for each pixel. And we take all images before and after 64 days of the fire. And we do that to avoid some of the impacts of noise from clouds, cloud cover, haze that may have been missed in the cloud mask. And then we predict this severity score with 5 categories. And so in Earth Engine, it's built so we only need those 2 bits of information, the fire polygon and then the date. And then we can map over all of the fires, because all of the fires in the database have the geometry and the fire date. So this is our study area, the Northern Jarrah Forest, and this is a specific bio-Eber region, and looking at open eucalypt forests and woodlands. And then you can see in that map C, pretty much the entire Northern Jarrah Forest has been burnt at least once in the last 16 years. Some areas 2 to 3 times, and that's from prescribed burns and wildfires. And then map D shows a collection of 64 wildfires and prescribed burns that I was able to then go to NearMap, which is a private company, and they provide aerial imagery with 3 to 7 centimeter resolution. I was able to find 64 fires with a post-fire image available. And then I went into those 64 fires and I defined different regions of the fire belonging to one of those 5 categories. And so I did that for about 11,000 pixels. It took a couple weeks, and those are for fires between 2010 and 2020. And then we eventually throw 34 of those fires, the severity scores, into a random forest. This is a supervised classification model, and then we predict one of those 5 categories. And so the predictor variables, these are different spectral indices computed from Landsat data, and some of the common ones like the normalized burn ratio and the normalized different vegetation index. I'm not going to go into these, but they're reflective, or they represent changes to quite a few different things, from vegetation to changes in soil cover or changes in charred material. And so the random forest is good with taking in a number of different predictor variables that may be correlated. In this case, these are probably all correlated, but they all represent a little bit something new to train the model for what it's looking for, in this case, severity. So I'll get into the model accuracy of those 30 fires that the model has not seen. So this is an independent testing data set that the model has never seen these fires, and this is for wildfires and prescribed burns. The overall accuracy, which is the number of correctly classified pixels divided by the total number of pixels, was about 84%, and that's for 5,612 Landsat pixels. And our accuracy is a little bit higher for wildfires, mainly because wildfires are mostly unburnt or very high severity categories. It's really the difficult part is predicting those category 2 and 3, which is burnt understory but unburned canopy. And it's pretty hard to see that sometimes, especially with closed canopy force. I show these confusion matrices, or error matrices for A, B, C, and D, which show wildfires, prescribed burns in autumn, winter, and spring. And what you see is for each matrix, on the x-axis is your observed fire severity, what I called it on the ground, or from the aerial photo. And then on the y-axis is the predicted fire severity score. So if we have a perfect classification, we'd have nice diagonal lines for each box. But you can see that rarely are we predicting across more than one category. For example, looking at wildfires, predicting category 2 and category 3, which is low canopy scorch and mid canopy scorch. Like I said, this is not easy to do in wildfires or prescribed burns. And I'd say that's a large source of our error. But we were pretty happy with these results, and we started kind of making spatial predictions of fires to see what these things look like. And so this is just two examples, one wildfire A and an example wildfire B. So wildfire A was majority category 4 and 5, very high severity. This was mostly happening in the summertime where it's much hotter, but again, this is we're just measuring the impact to forest canopy. And we're able to detect these kind of low severity patches on in this case on the northeast part of that fire, and kind of accurately depicting these burnt understory but unburnt canopy. And then the inverse also works for prescribed burns. So prescribed burn, that's majority category 2 and 1 to 3. This is low severity. We're also detecting some of these high severity patches, in this case on the eastern part of that fire. So these would be crown scorch or reaching the crown fires. Just to visualize, getting close. This is actually the wildfire from earlier 2021, the Waterloo bushfire, and we show two of our predictor variables, which is our normalized difference vegetation index and our DNVR scores, which are representing changes in vegetation and changes in charred material, and then we provide our predicted severity score. And then on the bottom left there, we have the area of each burnt severity category in square kilometers. Just to visualize, drive the point home, we're doing pretty well at picking up these within stand changes in severity patterns. And so quickly, some of the benefits of Earth Engine and how the tools over there made a lot of this possible. So in Earth Engine, we can access pretty much every Landsat image that's available to us. Surface reflectance ready to go, analysis ready data. And we have about a little bit over 700 fires. And for each fire, we use about 12 Landsat images. And that's about 8,400 images that I don't have to download and process myself. And to compute all those spectral indices, that's all done on Google servers, and I never see none of the data is actually touching my laptop, other than through some JavaScript or Python. So I mean that's alone like massive, because anybody with a basic laptop with Google Chrome or whatever browser can run the analysis, and it's built. This tool set is built so you can access all those data. You can process. You can do all your pre-processing, all of your model building, whatever it is, and then train your model and then predict with your model, all in the same environment. Again, never having any of the data touch the computer, and so it's a one-stop shop to do your whole analysis. And obviously they've built it that way on purpose. And then finally, there are many options for visualizing your data. And so you can visualize the data in the code editor, which is very nice. You can use like Jupyter notebooks, some other open source mapping libraries in Python, and bring those into a notebook and visualize your fires, or make plots of your data, whatever it is. And then there's also opportunities to make apps for users to visualize your data without actually having to mess with the data at all. So this is just one example of the of the outputs of this model. And so from here, we want to make, this paper is currently being reviewed, but if it's published, hopefully, we'll make the app fully available, and also all the rasters that we've created to be easily accessible and downloadable. So then if anyone is trying to ask questions about, like cockatoo habitat or, honeybee habitat, whatever it is, they can then, they'll have access to the polygons from DBCA data, but then they can also access the predicted severity scores. So I think that's a nice kind of segue from the earlier presentation, where it's like we're taking data that was made open source, and then we're kind of processing it. We're like sending it through this washing machine or some sort of processor, and then we're spitting out some other stuff on the end to give users more data, available. That is the end of the presentation. So go check out the flowering paper if you're interested, and hopefully this fire paper soon, and then hopefully sometime next year a paper linking the two, looking at these relationships between fire and forest phenology. And quick thanks to my supervisors in the CRC for honeybee products, which funded the research. Thank you.